if you're lucky, and I won't discuss this very much, but you can be lucky, it might turn out that you can find a particular line. See this, you're in part of your volume here. I'm just drawing one edge of it. But there could be a particular line that starts here and ends exactly at the other point. So basically, I'm here, and I have my gun, and I can shoot in unstable directions. If I do it in stable directions, I shoot myself. So I shoot in unstable directions. So something goes out, whoop, and I'm in 30 dimensions, 100,000 dimensions. If I'm in a plane, I have a good chance of hitting a point. If I'm in a three-dimensional volume, it's a little bit harder. I throw a boomerang, it's not so easy. The higher dimension, it's impossible to hit a point. Yeah. You can hit the volume, but hitting a point gets very hard. So shooting a high dimension seems extremely hard. So it seems it would be impossible to find a direction where I shoot in this neighborhood, space is curved and it goes down, it hits exactly the other point. However, it turns out it could be quite possible because this guy has a stable manifold which sucks up the whole volume of points. So if I can just somehow get myself into the stable manifold, the other guy, which is much easier because stable manifold is the dimension, it's a big dimension because the whole space is divided in the number of unstable directions and number of stable directions. So if I have one unstable but he has 9 stable directions, it might be very easy to fall into that hole. And that's an insight due to Poincaré again, which is called heteroclinic. Hetero meaning different. If I go from one point to another point and I hit another point, then I have a connection between two different points. So I don't know what clinic means, but this is a heteroclinic connection. If I have a fixed point and I shoot along the unstable direction, and I manage to fall into the stable manifold, so I shoot along here, do something, and manage to come back along the stable direction, that's called homoclinic. So that says that if I'm clever enough, I might be able to connect these neighborhoods exactly invariantly topologically connected, and once they're topologically connected, there's no way to disconnect them, because once you have a curve going from one neighborhood to the other one, no matter how you change your coordinates, that curve has to be there unless you destroy the continuity of space, but that's a bad coordinate change. So that's the way you can go from the local stability using unstable manifold and start constructing a global structure that you can see, because there are points and there are lines and it's embedded in lots of dimensions, but that you can see. And that guarantees that if I'm this neighborhood, I have a likelihood to visit another neighborhood. Because if I have one heteroclinic connection going from this neighborhood, then there is a neighborhood of these guys that follows it for the time that I want to follow it. So this starts enabling me to construct a chart saying, this is a big world, there's Japan, China, but if I go this way, I end up in China, and if I go that way, I end up in Atlanta or whatever. And the set of these mappings that I have is topologically invariant, and they connect invariant objects which have invariant properties, like they have invariant shearing and stretching rates in the neighborhoods. So that's good news. Good news. Now there are bad news. And I'm about 2 minds about the good and bad news. You know these heteroclinic connections already, because if you're playing some kind of game on a curved surface, you know that if you send the ball just the right speed and angle, it might go to the top of a hill and stay there. But it'll take infinite time. So, You might be able to do it because at the top of the hill has zero velocity and it's a smooth kind of thing. So if you overshoot at the top of the hill, it'll speed through at finite time. If you undershoot, it'll go and come back. But when you're exactly hitting it, it'll slow down and it'll take infinite time to get there. So in practice, me and my colleagues like the idea of heteroclinic connections, being able to get from here to there, but we're having lots of trouble of understanding how to really do this, because these are very special infinite length trajectories in time. Topologically they're very nice, but they're kind of hard to compute, because when you have an unstable system, computing something for infinite time makes it rather hard to do it well. In practice, this is a very good guide about how neighborhoods are connected, but we find periodic orbits much better. Periodic orbits have a property that never slow down, because if periodic orbit ever developed velocity zero, it wouldn't be periodic orbit, it would be a heteroclinic connection, because that's the definition of heteroclinic connection. It's a curve that goes to equilibrium, because at equilibrium there is velocity zero. And periodic orbits, by definition, have monotonely non-zero velocity every place. So these ones are actually much better guides to neighborhoods, because what they do is they zoom through a set of neighborhoods without ever stopping. So we take a tour and we come back. This is the deep idea, but we don't really know how to implement it as computation. Well, as I'll show you, exploring things by dynamical invariant sets like periodic orbits will be very good.